Our planet, Earth, has a long and ever-changing history. Over billions of years, its climate has constantly changed, swinging between periods of intense heat and frigid ice ages. Understanding these past temperature changes is really important. It gives us context for our current climate change and helps us predict the planet's future. Imagine Earth's history as a giant tapestry. The threads of this tapestry represent temperature fluctuations, woven together over countless years. By studying these threads, we unravel the story of Earth's climate. We can pinpoint periods of dramatic change, like the rise and fall of the dinosaurs. We can identify the events that triggered mass extinctions, forever altering the course of life. Scientists have discovered that Earth's average surface temperature has fluctuated between 11 and 36 degrees Celsius over the past 500 million years. By combining data on prehistoric temperatures with climate models, researchers at the Smithsonian National Museum of Natural History, the University of California, and the University of Bristol in England have created a 485 million year history of Earth's ever-changing climate. The new research was published in Science on September 20th. Working on the research since 2018, the scientists constructed the temperature curve to understand how Earth's climate has changed over the past 539 million years, a period of time experts call the Phanerozoic. The idea of creating a robust and reproducible record of Earth's climate history with a holistic view has received support, said climate paleontologist Emily Judd of the University of Arizona, who joined the project in 2020 to create a deep climate record of Earth, using both geological data and climate models. The researchers estimated prehistoric temperatures in a number of different ways. Among them, they looked at ice cores, which have air bubbles trapped inside. The chemical makeup of these air bubbles holds clues to the ancient climate at the time. Oxygen isotopes in layers of rock and prehistoric fossils can also be compared to each other to estimate whether Earth was warmer or colder at a given time. Even the structure of fossilized leaves can act as temperature proxies. For example, a leaf with smooth edges and a long drip tip for water to run off its surface suggests a warm, wet environment, while plants from colder climates tend to have serrated edges and no drip tips. Different times and places provide different kinds of evidence. The first step was to gather all the existing evidence. Together with a few dozen members of the paleoclimate community, we built a database with more than 150,000 estimates of ancient temperature, said Judd. This project was published in 2022. To build the big picture, project collaborators at the University of Bristol in England ran more than 850 climate model simulations of conditions during the Phanerozoic. By combining the temperature estimates and climate simulations, the researchers created a broader view of when the ancient Earth was relatively warmer or colder. The results cover Earth's temperature over the last 485 million years, the majority of the Phanerozoic eon, including a span of time that saw the early explosion of animal life in the oceans, the emergence of plants on land, and several mass extinctions. The analyses revealed that Earth's average surface temperature fluctuated from 11 to 36 degrees Celsius during the Phanerozoic, with the planet generally residing in a range of temperatures much warmer than today's. This will be a really useful record, said climate paleontologist Benjamin Mills of the University of Leeds in England, who was not involved in the new research. Not only is the study an improvement on previous methods, but it also points to Earth's climate being sensitive to carbon dioxide. More research is needed to understand more about the history of that sensitivity. The warm temperatures over the last 485 million years are tied to carbon dioxide. As atmospheric carbon dioxide increased, so did temperatures. This connection is especially apparent around some mass extinctions, when Earth's climate rapidly shifted in response to events like massive volcanic eruptions that spewed huge amounts of carbon dioxide into the atmosphere. The stable global temperatures and CO2 levels before the extinction are important, as this is the environment to which the organisms of the time were best adapted, noted Mills. Adding that with rapid changes in carbon dioxide and temperature creating stressful conditions that Earth's biodiversity struggled to keep up with. The rate at which Earth's climate is warming is particularly worrisome. The rate of climate change plays a key role in the ecological outcome, said Judd. Warming that takes place over millions of years forces organisms to migrate, evolve, or go extinct. But adaptation to warmer temperatures is possible. What humans are doing now is akin to moments like the end Permian mass extinction, when massive volcanic eruptions dumped huge amounts of carbon dioxide into the atmosphere and caused the worst mass extinction of all time. According to Judd, paying attention to Earth's temperature is essential to the survival of human society. The reality is that humans evolved and thrived under colder conditions, often in places near sea level, that are increasingly inundated as the warming climate causes sea levels to rise. Earth's resilience does not directly translate to our own capacity to adapt and thrive in the face of human-caused climate change. According to the research team, Earth is at a point where any action to limit human-caused warming is necessary. The story of Earth's temperature is not merely a tale of the past. It is a narrative that continues to unfold, with profound implications for every living being. Around 540 million years ago, Earth entered a new chapter, the Phanerozoic Eon. This period marked a major turning point in our planet's history, characterized by an explosion of life. The Cambrian explosion, as it's known, witnessed the rapid diversification of life forms, from simple organisms to complex multicellular creatures. The Phanerozoic Eon saw the rise of land plants, the evolution of insects, and the emergence of dinosaurs. This era was not without its challenges. Climate played a crucial role in shaping the evolution of life. Periods of global warming and cooling influenced the distribution of species. These changes also drove evolutionary adaptations, leading to the incredible biodiversity we see today. How do we know what Earth's temperature was millions of years ago? Scientists have developed ingenious methods to act like ancient thermometers, piecing together the puzzle of Earth's past climate. One such method is studying ice cores. These cylinders of ice, drilled from glaciers and ice sheets, trap ancient air bubbles within their layers. These bubbles act like tiny time capsules, preserving the chemical composition of the atmosphere from the time they were formed. By analyzing the ratios of different oxygen isotopes in these bubbles, scientists can estimate past temperatures with remarkable accuracy. Other methods involve analyzing the chemical composition of ancient rocks and fossils. For example, the ratio of oxygen isotopes in the shells of marine organisms can reveal the temperature of the water they inhabited. The carbon connection, a delicate balance. Carbon dioxide, a naturally occurring gas, plays a crucial role in regulating Earth's temperature. It acts like a blanket in the atmosphere, trapping heat from the sun and warming the planet. This is known as the greenhouse effect. Over geological timescales, the concentration of carbon dioxide in the atmosphere has fluctuated, influencing Earth's climate. For instance, during periods of intense volcanic activity, massive amounts of carbon dioxide were released into the atmosphere, leading to global warming. Conversely, the burial of organic matter, such as dead plants and animals, removed carbon dioxide from the atmosphere, contributing to periods of cooling. The balance of carbon dioxide in the atmosphere is a delicate one, and even small changes can have significant impacts on Earth's climate. Cataclysmic events. When life on Earth faces extinction, Earth's history is punctuated by periods of intense upheaval where life on Earth faced catastrophic challenges. These events, known as mass extinctions, resulted in the disappearance of a significant portion of species on our planet. While the causes of these extinctions are complex and multifaceted, climate change has been identified as a major contributing factor. One of the most well-known mass extinctions occurred around 252 million years ago, at the end of the Permian period. This event, often referred to as the Great Dying, wiped out an estimated 96% of marine species and 70% of terrestrial vertebrate species. Scientists believe that massive volcanic eruptions triggered a cascade of environmental changes, including rapid global warming, ocean acidification, and widespread oxygen depletion in the oceans. These changes were too extreme for many species to adapt, leading to their demise. Echoes of the past. Lessons from ancient climate change. Studying Earth's past climate is not merely an academic exercise. It holds crucial lessons for our understanding of present-day climate change. By examining how Earth's climate has responded to changes in the past, we can better predict how our planet might react to similar changes in the future. For example, studying past warming events, such as the Paleocene-Eocene thermal maximum, provides valuable insights into the potential consequences of rapidly releasing carbon dioxide into the atmosphere. These ancient events serve as cautionary tales, highlighting the potential for abrupt and irreversible changes in Earth's climate system. They remind us that our planet is capable of undergoing dramatic transformations with profound implications for all life on Earth. Our climate future. Learning from Earth's history. As we face the challenges of climate change today, the lessons from Earth's past are more relevant than ever. Earth's climate system is complex and interconnected. Changes in one part of the system can trigger a domino effect, leading to unintended and often irreversible consequences. Understanding how Earth's climate has changed in the past allows us to make more informed decisions about the future. By studying past climate events, we can better predict the potential impacts of human activities on the planet. This knowledge empowers us to develop effective mitigation strategies, reduce our carbon footprint, and transition to a more sustainable future. The story of Earth's temperature is a reminder that we are not passive passengers on this planet. We are active participants in shaping its future. By learning from the past, we can navigate the challenges of the present and create a more resilient and sustainable future for generations to come.